This is lecture 28. Today we will be talking about percent composition and empirical formulas. We're going to start out today by talking about chocolate. So right here I got a picture of some white chocolate, some milk chocolate, and dark chocolate. So these are all different types of chocolate, but what makes them different? Why do we have these different types? Well, it turns out in dark chocolate, you have more than 50% cacao coming from the cacao bean. And then you've also got some sugar and some cocoa butter. With milk chocolate, you've only got about 10% cacao, and you've also got sugar, cocoa butter, and milk. And then for white chocolate, you actually have no cacao. It's not really chocolate. You do have some cacao butter in there, but you also have then sugar and milk. So the big difference in these different types of chocolate is really the percent of cacao that's in there. And so we're talking about these to illustrate what percent composition means. So these all have different compositions. And if you had, let's say, 90% cacao in a chocolate bar, that would mean 90% of that bar is made of the contents of a cacao bean. All right. So this is composition in a broad view. We're going to get into much more specifics and talk about specific compounds. So what we're really going to be interested in is the percent composition of different compounds or materials, and specifically the percent composition usually of different elements. So the way we find the percent composition is just by taking the mass of an element that we're looking for, divide it by the total mass of a compound, and then times it by 100%. And that gives us the percent composition of an element in a compound. So if we wanted to figure out, for example, what the percent by mass of iron in Fe2O3 is, so the percent composition of iron in Fe2O3, what we'd do is just assume we're working with 1 mole of Fe2O3, right? If you worked with 2 moles, the math will work out similarly, but you'll have to multiply everything by 2. So if you just do 1 mole of Fe2O3, then we're going to calculate the molar mass of Fe2O3. This is something you've been doing all along, right? You take 2 times the mass of iron plus 3 times the mass of oxygen gets us the molar mass of Fe2O3. But then we're also going to individually calculate the mass of iron present. So here, right, we have 2 irons. So we'll take 2 times the mass of iron, which is 111.69 grams. So there's that much iron in 1 mole of Fe2O3. You'll notice that this calculation, 2 times 55, is just a part of this total calculation. And that's exactly what it's supposed to be. So we're just calculating the percent of a part of this thing. So then we'll take this mass, 111.69, divide it by the total mass of 159.69, and then of course times that by 100 to figure out that this is 69.9% iron. So now we've figured out the percent composition, or at least the percent of iron present in this. So we could then do the same thing for oxygen, right? Figure out the percent composition of oxygen, or we could just do 100% minus the 69.94%. That'll tell us how much oxygen is present. I'm going to give you a chance to practice this really fast. I want you to figure out for me the percent composition of carbon in propane. So propane is C3H8 here. So go ahead and pause the video and try and do this. All right, so the first thing we do, right, calculate the mass of propane. So there are 3 carbons, so 3 times 12, plus 8 hydrogens here. So 8 times 1, add that all together, and we get a total mass of 44 grams. And this would be 44 grams per mole. Then we figure out how much carbon is here. And I'll point out, I didn't report this in grams per mole because we're just going to be dividing grams by grams at the end. Then I'll figure out just the mass of carbon here. So there's 3 carbons, so 3 times 12, right? Still just part of this top equation where we figured out the mass of propane. So the mass of carbon that's here, 3 times 12 is 36 grams. And so what we'll do for calculating the mass percent is take that 36, divide it by 44 times 100, and get 81.715, which is about 82% here. I'll give you another practice problem here. If I've got these molecules down here, I want you in this time to tell me which has the highest percentage of carbon by mass. So not which one has the most carbon, but which has the most carbon by percent mass. Go ahead and pause the video and try and figure this out. All right, so what we're doing here, right, is we're figuring out the mass of carbon present in each of these, and then we're going to divide that by the total mass. So for A, D, and E, these all have one carbon, so they'll have a mass of carbon of 12. For B, it's got 2 carbons, so that'd be a mass of 24, and C, it has 3 carbons, so a mass of 36. So I've got those masses of carbons listed here on the left, and then I'm going to divide each of those by the total mass. Now I'm not going to go through and add up the total masses of all of these here, but I have them listed in these fractions. So for the first species, we've got 12/16, so that'd be 12 divided by 16 times 100%. But that's a ratio of 3 to 4. So carbon makes up 3/4 of the mass here. In B, carbon makes up 4/5 of the mass, which is slightly more than 3/4. In C, carbon is making up 9/11, which is also greater than 4/5. And then for CO2 and CO, carbon makes up 12/44 and 12/28 of the mass. Both of those are less than half of the mass. So the answer here is going to be C3H8. Now, if I had multiplied these by 100% and figured out the exact percentage of each of these, you can do it that way as well. Since I really don't care about the exact percent composition here, I'm really just looking for which one has the most. I got to skip that step. All right. How do we find then the percent composition of a compound if we don't already know its chemical formula? Right? So if we don't know its chemical formula, we're first going to have to figure out its chemical formula and then back out its percent composition of each. So if we're dealing with a hydrocarbon or other compounds that combust, we can actually just burn it. We can do what's called combustion analysis. And then in a combustion analysis, you're going to have this reaction where you're burning it, you're converting all the material into other stuff, and then you can analyze what's coming off of that, look at the stoichiometry of it to figure out how much carbon, hydrogen, oxygen, etc. is present there. Let me show you how this works. So in a simple experiment, let's say we're looking for a molecule we know just has carbon, hydrogen, and oxygen. If we burn it, we'll burn it in this special container. We'll weigh the mass of it before we burn it, so we know how much we're burning. And then as it's burning, we'll blow oxygen over it so that any gas that's released interacts with the oxygen, and also the oxygen can act as a flame source here, or a fuel. And then this stream of gas, though, will then go through an H2O absorber and a CO2 absorber, and you can have other absorbers farther down here. But so if all of our hydrogen in this is turned into H2O, it'll all get trapped in this H2O absorber, right? And then we can just measure how much heavier did our H2O absorber get in this reaction. That'll tell us how much water got trapped there. And then all of our carbon, if it gets turned into CO2, then it can get trapped in the CO2 absorber. And then anything that's left over, if we know there's just carbon, hydrogen, and oxygen, we can figure out how much hydrogen there was from the H2O absorber, how much carbon from the CO2 absorber, and then any mass that's unaccounted for would belong to oxygen. Now, why doesn't combustion analysis give you the percent oxygen directly like it does for hydrogen and carbon? Well, the reason is because we're pumping oxygen in here, we're reacting the hydrogen with oxygen, we're reacting the carbon with oxygen, so we're actually kind of flooding this whole system with oxygen. And I'll point out too that, so this would let us just look at things with hydrogen, carbon, and oxygen. If there's other things like sulfur or nitrogen, you can also put NO2 traps, SO2 traps, or various other traps to trap the specific element you're looking for. Now this looks somewhat straightforward, but it's actually a little bit complicated in practice. So let's look at a practice problem. Let's say we're working with aspirin, and we have 0.236 grams of aspirin. That's what we put in our furnace. and it's burned in oxygen, and we collect 0.519 grams of carbon dioxide. Now you'll notice there that I got more carbon dioxide out than aspirin that I put in, right? So the reason for this is because we're releasing carbon from the aspirin, but the carbon is being converted to CO2. And carbon only makes up a fraction of the mass of CO2, right? So from this mass of carbon dioxide, we can figure out how much carbon was burned off. So to do that, we take this 0.519 grams of carbon, we divide it by the molecular weight of CO2 to get into moles of CO2 that are produced. And then what we need to do is go from moles of CO2 to moles of carbon, because we're only interested in carbon. And in this case, there's only one carbon per CO2 unit, so the fraction there of the ratio between moles of carbon and moles of CO2 is a 1-to-1. And then we can multiply by the molecular weight of carbon to find that we actually only released 0.142 grams of carbon from this thing, right? So if we know that's how much carbon came off, we can then divide by this 0.236 grams to figure out what percentage of the aspirin is carbon. And we find that it's 60%. All right, so I jumped the gun a little on this question. Let's finish reading it. So there's also 0.094 grams of water formed. And now it wants us to figure out, the question wants us to figure out how much carbon, hydrogen, and oxygen percent-wise in this aspirin. So we've already figured out the carbon. Let's take this water amount and figure out how much hydrogen is present. Now, hydrogen, right, is trapped in the form of water. But of course, hydrogen only weighs 1 AMU, whereas oxygen weighs 16. So hydrogen is actually not going to make up the bulk of this mass. So let's convert to grams of hydrogen from grams of water, right? So we'll take the grams of water, divide it by 18, then we'll multiply it by the mole fraction. So there's actually 2 moles of hydrogen in here for every 1 mole of H2O, right? So we'll have to multiply that by 2, then multiply by the molecular weight of hydrogen to find out that we only released 0.0106 grams of hydrogen. And again, we'll divide by the total mass of the aspirin times by 100% to get 4.48% hydrogen. Now, in this question, we're assuming we know that all that's present is carbon, hydrogen, and oxygen. And so then oxygen is just going to be whatever is left. By that, I mean we started with 100% of the material, 60% was carbon, 4.48% was hydrogen, and that must mean that 35.5% is oxygen by mass. Okay, so we've broken aspirin down into its components, its percent composition here. But now how do we go from that percent composition to a chemical formula, right? There's not 60 carbons in here for every 4 hydrogens, and there's not 35.5 oxygens anywhere, right? So what we're going to have to do is figure out our mole ratio. So we know this molecule is going to be of the form CXHYOZ. We just don't know how many carbons, so we don't know the value of X, we don't know the value of Y or the value of Z here, right? So what we're going to do is change each of these percent compositions into grams first off. So we'll assume just for ease that we're dealing with 100 grams of aspirin. Now it doesn't matter how many grams we actually started with. You're generally always just going to start with, or for this calculation, always just use 100 grams of whatever you're using. The reason you do that is because 100 grams times 60% becomes 60 grams. So the math is really easy there. Then once we have these grams, we're going to convert the grams into moles, right? So for carbon, you have 60 grams divided by the molecular weight of carbon gives you 5 moles of carbon. For hydrogen, we'll take 4.48 divided by 1.0079, which gives us 4.44 moles of hydrogen present. And then we'll do the same thing for oxygen, take 35.5 divided by 15.99, etc. And we'll find that we have 2.22 moles of oxygen. Okay, now we have a ratio of all of these. We have a ratio of 5 carbons to every 4.44 hydrogens to every 2.22 oxygens. We can't, though, in this formula, X, Y, and Z can't be fractions. We've got to get them into whole numbers. So the easiest way to do that is actually to divide by the smallest number of moles here. So oxygen has the fewest moles, it's got 2.22. So if we just divide all of these by 2.22, that gets us down to 1 mole of oxygen, 2 moles of hydrogen, and now 2.25 moles of carbon. Okay, so we've simplified this a little bit, but we're still stuck with a fraction. And now if there's any fractions left, we'll multiply all of these numbers by a given number so that that fraction will become a whole number. So this is 2.25. To get 0.25 to be a whole number, we're going to have to multiply it by 4, right? So 0.25 is 1/4. Multiply that by 4. So we'll have to multiply all of these by 4. So 2.25 times 4 is 9, 2 times 4 is 8, and 1 times 4 is 4. So now we've got the formula of aspirin, which is C9H8O4. So this is our actual structure of aspirin. And if we count, we've got 1, 2, 3, 4 oxygens, and 1, 2, 3, 4, 5, 6, 7, 8, 9 carbons. And we won't count hydrogens, but you can see that the formula there is correct. Now, there is a problem here. There is a problem, and it can actually be a big problem. Historically, until probably 50, 60 years ago, this was a big problem. And that's that this value that we just found is what we call the empirical formula. When we say empirical, so if we have empirical data, that means it's experimental data. It's not something we came up with from a theory, it's hard measured values. Now, the empirical formula is the lowest whole number ratio of elements, but that's not actually always the chemical formula. So to give you a great example, benzene here has a molecular formula of C6H6, right? You've got these 6 carbons, each has 1 hydrogen atom. If you do combustion analysis of benzene and find its empirical formula is just going to be CH. So for a long time, it was very hard to go from the empirical formula to actually figure out the molecular formula here. You'd have to do a lot of different experiments, and it was very hard. But before we get on to how we jump from the empirical formula to the molecular formula, I'm going to point some really important things out. The empirical formula does not always equal the molecular formula. They're not always the same thing. But the one thing that we do get that's nice is the molecular formula is always some whole number integer times their empirical formula, right? So in this case, our molecular formula is 6 times our empirical formula. So it always has to be a whole number multiple of our empirical formula, which makes our lives a lot easier. So before we get into too much more of that, though, I'm going to give you a combustion reaction here. So in this combustion analysis, this is of nicotine. We find that nicotine consists of 74% carbon, 8.65% hydrogen, and 17.35% nitrogen by mass. And I want you to find for me the empirical formula of nicotine. Go ahead and pause the video and work on this. All right, so first, let's assume we have 100 grams of nicotine. Figure out how many grams of each of these we have. So we have 74 grams of carbon, 8.65 grams of hydrogen, and 17.35 grams of nitrogen. Convert all these into moles, right? We divide grams of carbon by 12, grams of hydrogen by 1, grams of nitrogen by 14. We find that we've got 6.16 moles of carbon, 8.58 moles of hydrogen, and 1.24 moles of nitrogen. Right? If we then divide all these by the smallest number of moles, which is 1.24 for nitrogen, right? We find that we don't really get whole numbers here. We get 4.97 and 6.92. But if they're really close to a whole number, like within plus or minus 0.01, or plus or minus 0.1, so all of these are within 0.1, we can generally assume that we can round that to a whole number. So why would these not be whole numbers? Well, usually just due to experimental error, some imprecision in the measurements that didn't get us the exact right value. But here now we can see that we have 1 mole of nitrogen, 7 moles of hydrogen, 5 moles of carbon. So the answer you should have got was A. So C5H7N. Now, unfortunately, that is not the actual molecular formula of nicotine. Nicotine's actual formula is C10H14N2, whereas the empirical formula is C5H7N. So the molecular formula is actually twice the empirical formula in this case. But how would we figure that out? Well, nowadays, it's actually much more easy than it used to be. Ever since the invention of what's called mass spectrometry, this problem has gotten exponentially easier. So in a mass spectrometer, what you can do is you send your sample through, and if it's and it'll interact with a strong magnet that'll turn your ions, and the amount that the ions turn, or the amount that your molecules turn as it goes through this magnet, depends on how heavy they are. So lighter things turn more, heavier things turn less. And then they come and fly and hit some detection plate. And based on where they hit, we can figure out what exactly they weigh. So we can now weigh individual molecules, and we get something that looks like this, which we call a mass spectrum. On the x-axis, we plot the mass. We actually plot it as mass divided by charge. So we can actually only see the masses of things that are charged, but it turns out it's not too hard to turn most things into an ion if you just put a bunch of electrons nearby. And then on the y-axis is just intensity. So right here is a really intense peak of what we'd call the molecular ion for a species. So this is actually the molecular ion for benzene, and it shows up at 78 atomic mass units, right? So this is the mass of a single molecule that we've weighed here. We can then compare this molecular mass that we found to the empirical formula mass. And if you'll remember, it's really easy to go between AMU, or atomic mass units, and grams per mole. All you have to do really is drop the AMU and add the grams per mole. So our molecular ion weighs 78 AMU, and we found from our empirical formula, CH for benzene, this empirical formula would weigh 13.02 AMU. So if we had one CH molecule, it weighed 13.02 AMU. And if you'll remember, our molecular formula is always going to be some whole integer value times our empirical formula. So if we're going to figure out how many times we have to times CH to get to the formula of benzene, we're just going to take the two masses, our molecular mass, and divided by our empirical mass, right? So this is the mass from our empirical formula, or the mass that we found in our mass spectrometer, divided by the weight of our empirical formula. And that gives us a value of about 5.99, which is about 6. So now we know that we have to take CH, multiply it by 6, so then we get C6H6. And that's all you have to do. So let me give you a practice here. Let's say we're looking at nicotine again. We found in the last problem that nicotine's empirical formula is C5H7N. Now I want you to compare that to the peak that we get in the mass spectrometer. Now the peak is at 162 grams per mole, or 162 AMU. I want you to tell me what the molecular formula of nicotine is. Go ahead and pause the video here and try and figure this out. All right, so first what we have to do, right, is find the mass of our empirical formula, C5H7N. If you do that, you find a mass of 81.1 grams per mole. If you take 162, divide it by 81.1, you'll find that that's a ratio of about 2. So that tells us we need to multiply our nicotine value by 2. So we have C5H7N times 2 is C10H14N2. So we get B is our answer. Again, here's the structure for nicotine. All right, so now we've taken a bunch of steps and broken them all down. But let's say I wanted you to go for the molecular formula from the percent composition. How would you do that? Well, to do that, right, you'd take your percent composition, your percentages, turn them into grams, Then once they're in grams, convert to moles by dividing by the molecular weights of each of the elements. Then once you have your moles, divide all by the smallest number of moles to get your mole ratios. If there's any fractions in your mole ratios, multiply all of them by a factor that gets you whole numbers for everything. Then calculate the mass of your empirical formula, right? So at this point, you have a working formula. It's not the molecular formula, but it is a multiple of your molecular formula. And then you're going to find your molecular ion mass from the mass spectrometer, compare that to your empirical formula mass to get you a value that you have to multiply your empirical formula by. And that will get you to your final value, your final molecular formula. So there's a lot of steps in there. You want to be able to master each of these steps along the way. If you can do that, then you actually have quite a bit of power trainings. All right. Let's say now, let's put this whole thing into practice. Let's say we've got vanillin. This is a compound that gives vanilla its taste, and it just contains carbon, hydrogen, and oxygen. Let's say we combust 30.4 grams of vanillin, and that produces 70.4 grams of CO2 and 14.4 grams of H2O. The molecular ion of vanillin on the mass spectrometer gives given above. So this mass spectrometry or mass spectrum up here gives us a mass of 152 for vanillin. And I want to know what are the percent composition in the molecular formula of vanillin. All right, first thing we have to do, figure out how much carbon was released here. So we got 70.4 grams of CO2. So we'll take 70.4 grams divided by the molecular weight of CO2, convert it to moles of carbon, then to convert it to grams of carbon. So we got 19.21 grams of carbon. Now we'll turn that into a percent composition. We started with 30.4 grams of vanillin. So 19.21 divided by 30.4 times 100 tells us there's 63.19% carbon. We'll do the same thing for our water. To go to hydrogen, we'll take the 14.4 grams of water that are produced, divide by the molecular weight of water, then go from moles of water to moles of hydrogen. So that'd be a 2-to-1 ratio. And then go from moles of hydrogen to grams of hydrogen. We find there's 1.61 grams of hydrogen there. Turn that into a percent composition. Now we've got 5.30% hydrogen. And then of course, for oxygen is the leftovers. So we take 100 minus 63.19 and 5.31 to find there's 31.51% oxygen. Okay, so now we've got the percent composition of everything. Now we need to turn this into an empirical formula. So we'll assume there's 100 grams of everything. Assume that we're dealing now with 100 grams of vanillin, turn all these into grams and then into moles. So we'll assume we've got 63 grams of carbon, which corresponds to 5.26 moles of carbon. Do the same thing for hydrogen. Say we've got 5.3 grams of hydrogen, that's 5.26 moles of hydrogen. Oh, look, those numbers are lining up. And we'll do the same for oxygen. For oxygen, we'll find that there's 1.97 moles of oxygen. Now, the next thing we got to do, right, divide by the smallest number of moles here, which would be oxygen. So we can get these into as closer to whole numbers. So we'll divide by 1.97 for each of these, and that gives us 2 2/3 moles of carbon, 2 2/3 moles of hydrogen, 1 mole of oxygen. Since we've got 2 2/3, we're going to have to multiply all of these by 3 to get us to whole numbers. So we do that, and now we've got 8 carbons, 8 hydrogens, 3 oxygens. So our empirical formula is C8H8O3, which weighs 152.15. If we compare that to our molecular ion peak, which is 152, we'll find that the ratio between our molecular formula and our empirical formula is 1. So I take our empirical formula times 1, and we get C8H8O3 as our formula for vanilla. Now you can see an entire experimental setup, all the experiments that need to be done, all the analyses that need to be done to go from vanillin to a formula for vanillin. All right, so we've actually got quite a bit of powerful step there. Now, one little drawback is that this technique we've talked about can't actually tell us differences, or can't distinguish between different isomers. So for example, structural isomers like vanillin, so this is vanillin on the left, the thing that's yummy, and there's something else called ortho vanillin that differs from vanillin only in the fact that this OH group is moved from pointing down to pointing to the upper right up here. Vanillin is really good. I actually like vanilla a lot. Vanilla ice cream is one of my favorite flavors. My family disagrees because they're all wrong. But ortho vanillin over here is actually pretty toxic. You don't want to be ingesting this or you're going to be making yourself sick. And it doesn't taste good. So if we're looking at vanillin and ortho vanillin, how are we going to tell these two apart? Well, we have to do further experiments. And actually mass spectrometry is really helpful in this, in that mass spectrometry actually is pretty harsh on molecules. It has a tendency to break them apart. And so oftentimes we won't only see the peak for the molecule we're looking at, but we'll also see a bunch of peaks corresponding to that molecule being broken into pieces. And once we break it into pieces, then we have the pieces, and then we can figure out, it's a lot easier to figure out the structure of smaller pieces, and then we can take those smaller pieces and put them together to figure out bigger pieces. So down here, in these mass spectrum down here, the top one is actually for vanillin, and this bottom one is for O-vanillin or ortho vanillin. And you'll notice that a lot of these peaks are pretty similar. We see peaks at 53 and peaks at 65 and 81. But you'll notice for the O-vanillin, for the regular vanillin, we get this big peak at 106. We don't see anything like that in the ortho vanillin. So using mass spectrometry and other techniques, you can tease out different isomers. That's actually a bit beyond the scope of this class. You're not going to have to be able to interpret a mass spectrum in this class. But mass spectrometry is actually what I do for my research, and so I think it's pretty fun and pretty interesting. Anyways, that's it for percent composition and empirical formulas. Let me know if you have any questions or you need any help.